quiet. We have started discussing Bayes classifier, and in the Bayes classifier we have assumed that each class conditional PDF is a Gaussian, and then we have derived the mu and the variance, right? The mean and the variance we have derived for a univariate Gaussian. So suppose in your Bayes classifier setting you have some label data given to you, and using that label data for each class we will fit a class conditional PDF. Okay, so based on the PDF or based on the parameters of this PDF, like during the inference stage or the testing phase, given the test sample, basically you will actually substitute in all of your class conditional PDFs, and whichever is maximum, you will, based on that you will decide the class for your test sample. Right? So this is how we actually formulated our Bayes classifier, and we have derived the expression for mu and sigma. Okay, so now if I ask you, this Bayes classifier, is it a linear classifier or a non-linear classifier? Is it a linear classifier or non-linear classifier? Suppose if your data is not linearly separable, if it is distributed in a way that it is not linearly separable, do you think your Bayes classifier will work in that case? Yes? Yes or no? Okay, we'll see. Like, you think about it, whether it is a linear classifier or non-linear classifier. See, it will become linear in few cases. You will actually end up getting a straight line in few cases, and in few cases you will actually get a quadratic function. Okay, so it is a non-linear classifier. Let's see how is it a non-linear classifier. Okay, so we have discussed the mu and sigma, and then we ended up getting these two expressions, right? For mu, it is just a sample mean. Okay, we actually we took our likelihood and we tried to maximize likelihood, and we found these expressions. Basically, we found the parameters such that your likelihood is maximized. Okay, so in yesterday's class there was a question, my maximum likelihood for my Gaussian, actually the mean, the mu parameter, it's simply equals to your sample mean and sample variance, right? So why am I even deriving this? When I actually started the derivation, I am actually formulating it as maximizing likelihood, and when you maximize your likelihood and derive your mu and sigma, you ended up getting mu as sample mean and sigma as your sample variance, right? Sample variance nothing but the whatever the observed sample given to you, you will be using them and finding your variance and mean. Okay, so now this mu is equals to sample mean and sigma is equals to sample variance in few cases only. Maybe for Gaussian it is true, and the exponential that you have tried, is it true in case of exponential? Lambda parameter that you have derived by maximizing your likelihood, is it equals to sample mean? 1 by sample mean? Yes. So it is holding for your exponential and Gaussian, and maybe for few other distributions, but in general it is not true. It is not always true that whatever the parameter that you estimate is equals to sample mean on sample parameters. There can be more complex distribution functions where this will not hold. Okay, so now the question is it always equals to sample mean? No, it holds for few distributions but not for all distributions. Fine. So now we have actually derived the variance, no? So I am saying that my variance estimated using my maximum likelihood is a biased estimate. Okay, so now we'll see what is the meaning of biased and unbiased estimates. Suppose if you are estimating a parameter, okay, if you are estimating a parameter and you are taking the expectation of your estimates, okay, so if you are taking the expectation over your estimates, if they are equals to your true, okay, then it means that your estimate is unbiased. Okay, not true, it should be always a constant value. Okay. So then if your estimate, if you take your expectation over your estimates, if it is not equals to a constant value, then it is biased estimate. So in your ML estimation for your Gaussian, when you are fitting your Gaussian on your class condition data or the class specific data, see you got your mu MLE and your sigma square MLE. Okay, so I am saying that your mu is unbiased and your variance is biased. Okay, so if there is bias in your estimation, you need to correct that bias. Okay, so we'll see what is like how is my mu unbiased. If you have, so this is your estimate, maybe based on the finite number of samples given to you, 1 by n xi. This is your sample mean, right, or the mu estimated. So to this I am applying expectation. Okay, so if I apply expectation, I can take my expectation inside. Yes, I can take it inside, no? So it is nothing but your n into maybe mu true or mu, which is your expectation of your samples, right? So then this is equals to your mu. So expectation of mu MLE is equals to your true mean. Yes, so this is unbiased estimate. Okay. Fine, it means that like you have some set of data points and you're sampling randomly and estimating one mu, and next time you're sampling randomly and estimating one mu. So you have like this maybe infinite number of mu or means with you, and if you take expectation over all of those means, then that is equals to your true mean. Okay, so this kind of like, and the way you are estimating is using your ML estimate. Okay, so if you are taking expectation over all mu's, it is equals to true mean, then this is unbiased estimate. Okay, so now I am saying that your variance is biased. You have seen this already? In data science 3 you have seen this already? No. Okay. So suppose if you have your expectation, so what is this MLE estimate? It is 1 by n, I is equals to 1 to n, xi minus maybe mu m. So instead of keeping MLE, I'll just keep it as mu hat, okay? Because the one I'm estimating, I'll just use the notation as mu hat. So this is the expression. So I'll just apply. Okay, so then I'll just apply my summation also. I'll just take it inside to each individual term. Then here my mu hat is independent of my summation. Xi plus 1 by into summation Now can I write this 1 by n and this summation as mu hat? Again, this 1 by n and this summation is my mu estimated again, no? So I can just remove the summation xi and n and I can replace it with mu hat. Okay, so then this becomes, here also this summation is independent of mu square. Okay, I can just write into n minus. Okay, this I can cancel. Sorry. This is 2 mu square plus mu square. Mu hat square. Okay, so now just take this expectation inside. Minus expectation of mu hat square. Yes, this 1 by n I already took it inside, and now I am taking this expectation inside the summation. Okay, so now this becomes, see the summation again, this is an expectation term, so the summation is anyway independent. So now I can write this as expectation of xi square minus expectation of mu hat square. Yes. Am I making any mistake? Fine. Now, just tell me what is the variance of xi and variance of mu hat. Can you tell me the variances of this? It is nothing but expectation of x square minus expectation of xi whole square. And this is, so variance I will just write it as xi like this. I'll just give this notation. And here expectation of mu hat square minus expectation of mu hat whole square. And this I am giving. Okay. So let's substitute these here, where your x square plus expectation of xi whole square is equals to expectation of xi square, and then mu hat square okay. So these two terms will substitute here. Minus sigma mu hat square minus whole square, right? Fine. So now your expectation of mu hat is equals to mu, because your mu estimate is a unbiased estimate. So here I can just replace it with mu, and here also I can just replace it with mu, and I can cancel these two terms. Yes or no? See, it is very simple. I'm just expanding the variance that I've started with, and I'm just using these variance formulas, and then I've substituted. And here I'm making use of the fact that my mu estimate is unbiased. Okay, so here this becomes mu x square minus mu sigma hat square. These two you can cancel out, right? Because expectation of xi is mu and expectation of mu hat is also mu. Because your mu is an unbiased estimate, no? So then this you can substitute and cancel these two terms. And now you actually ended up getting this. Expectation of your MLE. Okay, so this is your sigma x square minus sigma mu hat square. Okay, so this is nothing but your variance for your mu hat, right? So how can I write this? So the variance of mu hat. So maybe mu hat is what? 1 by n summation I is equals to 1 to n xi, right? Your mu hat is MLE estimate, right? So that is this summation. Okay. Then this becomes, if I have to take my variance inside, variance of AX is what? Where x is a random variable, a is a scalar. Variance of AX is what? A square into variance of x, right? So this is 1 by n square into variance of summation I is equals to 1 to n xi. Okay. So this variance of x plus y plus z is equals to variance of x plus variance of y plus variance of z when x, y, z both three are independent, right? So now I am assuming my samples are independent and identically distributed. So in that case I can take my variance inside and I can just write it like this. Okay, so this becomes your variance of xi when I assume independence, right? If I assume independence, then this becomes this. So now your sigma x square minus n square. Yeah. So this you can write it as variance of x square because it's just the true variance. Now this becomes, here the summation is again independent. You can just write it as n into sigma x square by n square, and this becomes your sigma x square minus 1 by n into sigma x square. Okay, this you can actually take it out. This becomes 1 minus 1 by n, which is your sigma x square into n minus 1 by n. So what is this? This is your expectation of your MLE estimate. Expectation of your variance, which is coming from your MLE estimate, if you compute, it is not equals to your true variance, right? You have a factor here. That factor is depending on your n value. So that's why you are saying that your variance is unbiased. Okay, sorry, biased. This is biased. Because you have a factor which is actually making this is your true one and this is your expectation of your estimated. So both are not true, both are not equal, right? Then this is biased. Now the question is, how can I actually fix this bias, or how can I do bias correction? Now can you tell me how can I do bias correction? I have my expectation. that is equals to true into some factor. Okay, so if I have to do bias correction, what should I do? What should I do? Just remove that factor, right? You have a factor term or this constant term which is depending on your n value, and that is getting multiplied with your true value, and that is equals to your expectation. Because of this, your estimate is becoming biased. So now you have to do bias correction. So, and now can you tell me, your variance is true value, no? Your estimated is coming like this. Now, using your MLE estimate, whatever the variance you are estimating, it is always lesser than your true variance. Can I say that? Based on this equation, can I say that my estimate coming from my MLE or the maximum likelihood is always less than my true variance? Can I say that? Is this factor always less than 1? Is this factor always less than 1? Because I am multiplying with a factor which is less than 1 to my true to get my my estimated. So now my if you have like your true as 5, maybe variance as 5, and this factor is multiplying 5 into some 0.9 or something, then you'll get lesser than 5, right? So here with this MLE estimation, your variance estimated is always less than your true variance. We can conclude this based on this expression, okay? And based on this expression, you can also say that your variance is biased. Okay, now I have to do bias correction. Okay, I have to basically remove this factor term. So then what should I do? To my estimated, okay, see this is my, like suppose if this is my estimate, to this I will just multiply with n by n minus 1. It's basically dividing with this factor. So I have to divide my estimate coming from maximum likelihood with that factor. Then only I can do bias correction. Okay, so dividing with this term is nothing but multiplying with n by n minus 1 into your estimation. Okay, so this is like maybe to correct for bias, you have to do this multiplication. So now can you write down the expression n by n minus 1 into what was the previous expression for your estimate? 1 by n, I is equals to 1 to n xi minus mu ml whole square, right? So this was your previous expression, and now you are doing the bias correction using this term. So after your bias correction, what is your MLE? As n n will cancel out, you will have 1 by s. Okay, so this is after your bias correction. Is this fine? In most of the textbooks, if you see, for your Gaussian distribution, when you are fitting your Gaussian on the data points for mu, and like when you are estimating mu, mean and variance, your variance expression will be like this. Have you seen this anywhere? In most of the textbooks, you will find n minus 1 instead of n. Okay, so that is after your bias correction. Is this okay? Do you have any doubts? What? Yes, because it is a Gaussian, you got your estimate as sample mean, and when you apply expectation on your estimate or the estimated one, you are actually finding out that that expectation is not equal to your true. You have a factor term, so that's why you are correcting for that factor. Okay. I don't know why are you smiling? What's happening? Is this clear? Fine. What is making you smile? Can you tell? Fine. So this is okay, right? The MLE estimate coming from your for your Gaussian is not biased in its true sense. Then you are correcting for it with a factor term. So after the correction, you are getting n minus 1 in the denominator instead of 1. Okay, so if you follow your previous procedure, or where if you use n directly, your estimate will be always lesser than your true estimate or true value. Okay, is this fine? Now if you want to prove it again, do one thing, take this expression, apply your expectation and verify whether it is equal to your true or not. If you want to verify this, right, this one, is it a biased or unbiased, apply expectation again and then derive and then see whether it is equals to true or not. I don't know why you are smiling. What is happening? Is this clear? Is this clear? Fine. See these two courses, right? In your data science 3, you will get exposure to a concept, and in your ISL, you will go deeper and you will try to derive things. So these two courses are structured like this. You might think that, okay, we know Bayes classifier, but there are many more things to know about Bayes classifier. Okay. Fine. Is this fine? Now shall we move forward and discuss our multivariate Gaussian. So in this previous case, I assumed that my Gaussian, I assumed univariate Gaussians, and I tried deriving expressions for my mu and my sigma, okay, specific to class 1 and specific to class 2. Now, what if my x, or the data point in each class, is d-dimensional? Okay, so in such cases, you need multivariate Gaussian. Okay, multivariate Gaussian, and which is a function of your parameter vector, mu vector, and your covariance matrix, right? So instead of having a single variance, now you will have a matrix, covariance matrix, and your mu vector. Okay, so ideally, if you have to fit, if you have two classes, assume that this is d-dimensional one, and then class 1 and XD class 2. So in this cases, you have to derive the expressions for this mu vector and sigma matrix. 1. Okay, so we have to estimate mu vector from your class 1 specific data points and covariance matrix. Now, for multivariate Gaussian, can you tell me the expression? I'll just write down, you just verify whether it is right or not. Is this right? Is this correct? Fine, this is fine. This is your distribution function for your d-dimensional case, right? So now, can you tell me when will this exist? When can I actually fit a multivariate Gaussian on a particular data set? When is this defined? So this particular expression has the term sigma inverse. If your sigma inverse doesn't exist, then you can't define your multivariate Gaussian on a particular data set. Okay, so what is your sigma? Sigma is your covariance matrix, right? And mu is your vector, mean vector. And the dimension of this is t cross t, and this is your d. Maybe 1 cross t or d cross 1. Okay. So now when will this exist, or inverse for your covariance matrix, when will this exist? Non-singular, yes. Okay, maybe let me ask you this way. When will your covariance matrix become singular? What are the cases? Determinant is 0. Dependent, yeah, that's nice. Dependent, you mean like what kind of dependency? Linear, what's happening? Is it okay? Fine. Dependence or linearly dependent? If your features are linearly dependent, then there is linear dependency and your inverse won't exist. And any other case, can you tell me any other case where your sigma matrix becomes singular on a particular data set? So maybe let me give you a hint. Okay, so first let's see how to find out your covariance matrix. What's happening? Are you discussing or? Okay, fine. Tell me the answer now. Still in discussion? Okay. So whenever you have more number of variables compared to your data points, suppose your dimension is d, okay? And you have some k number of samples with you. And k is less than your d. Dimension is higher, but the number of data points that you have are maybe lesser than the dimension. So in such cases, I am saying that your covariance matrix may become singular. Do you agree with that? Because you don't have enough samples to estimate that full rank matrix, right? So in such cases also your matrix may become singular. Okay, maybe like to get more clarity, right? Just go back and find, not now, just take these two vectors. Okay, assume that this is your data point 1 and data point 2 and your dimension is 3, but you have only two samples with you. Okay, just go and find the covariance matrix using these two samples and see what is happening to your covariance matrix. Okay, so you will get a covariance matrix. How will you find the covariance matrix given the data points? Your covariance matrix is what? X minus mu, right? Something like this. First you have to mean normalize your data. And you know why are we doing the mean normalization also, right? Without doing mean normalization, if you compute covariance, what will happen? If I don't want to do mean normalization. Without mean normalization, if I directly compute this, what will happen? We have seen the impact of mean normalization, no? Without mean normalization, if you do, what happens to your regularization problem? You will get that weightage issue, no? No? Okay, fine. See, this is how you compute your mean vector and your covariance matrix. After doing the mean normalization, we'll compute the covariance matrix, and you have to answer, you have to go and see, without mean normalization, if I compute my covariance, what will happen to my covariance matrix? Will it be a correct estimate or not? Okay. Fine. So my covariance will become singular in two cases. One is your linear dependency, and another one is where when you have very less number of samples compared to your number of variables or the dimension. Okay. And any other case where your singular matrix becomes, where your covariance matrix becomes singular? Any other case? What? Okay, so variance of, it means that you have a constant features. Okay, maybe your data set is corrupted and you have a constant feature in a single dimension. That's good. That's also one possibility. Yes? Two are highly correlated. See, correlation can happen. Two variables can be correlated if there is a nonlinear dependency also. So that is linear dependency, no? So that is already done. We have discussed that. We are saying that linear dependency in this one reason, and the second reason is you have less number of data points. Maybe the third one, what she was telling is you have variance, like a fixed feature or fixed constant value in a particular feature. Okay. Fine. So when your covariance matrix is singular, you can't define your multivariate Gaussian. Okay. Either you have to do some dimensionality reduction to fix that issue, then come back and fit your multivariate Gaussian. Okay, or else you have other advanced Gaussian fitting methodologies which can handle these issues also. But whatever we are going to discuss, the simple MLE estimate for your multivariate Gaussian will not handle that. You have to fix your data, or you have to remove your linear dependencies. Then only you can fit your multivariate Gaussian. So how to fit your multivariate Gaussian is a question now. Okay, so how to learn these two parameters given your data points? Okay, so if you have your data points, the first step is to write your likelihood for your entire data set, assuming that okay, so this likelihood may be is a function of this likelihood we have to maximize with respect to mu and sigma, right? So let's derive that. But before we derive, we will just see how your covariance matrices will be for different combinations. So if you have a two-dimensional multivariate Gaussian or a bivariate Gaussian with two dimensions, if your variance along both the dimensions, if it is equal, then your contour plot will look like this. Okay, and if you have variance 1 is higher than variance 2, then it is something like this, and where your variance 1 is lesser than variance 2, then you have a contour plot like this. Okay. Yeah, so if you have like the same, just a diagonal matrix, it means that the variance along both the components is same, but I mean the variance is different, then it will actually reflect in your contour plots. Okay, so now, if you have your covariance between feature 1 and feature 2, if they are positive, then it will actually reflect like this. You have the contour plot of that bivariate Gaussian will look like this. It is a positive correlation and this is your negative correlation. Okay, so here if you see your feature 1 and feature 2 still correlated, but still my covariance matrix actually it exists and we were still able to fit a multivariate Gaussian for it. Okay, so I am not saying that before you go and fit your multivariate Gaussian, I am not saying that you make your data points completely independent. No, there can be some correlation. So there is a difference between correlation and your linear dependence. I am saying linear dependency will create the issues, but not the correlation. In your first class you have seen, right? There was a take home question where I am trying to ask you if there are two random variables, if they are correlated, does that imply independence? Or the independence, does that imply correlation? So now maybe after this class your task is go, like if you see, if you have two features, go and see like if they are linearly dependent, what will happen to my covariance, and if they are correlated. Correlated meaning not just the linear dependency, no. It can have quadratic dependency, it can have, suppose if you have like x1 and x2 and x3. Okay, if you have like this as x and this as 2x and this has maybe 3x, then you can say x1, x2 and x3 are linearly dependent on your x1. But suppose if I have some x cube here and x square here, they are not linearly dependent, but still they are correlated, right? So the problem for us is our linear dependency. Okay, so now you have to go and see what happens to my covariance matrix when there are quadratic dependencies and when there are linear dependencies in my data set. Okay, which will create problem and which implies what? Okay, is this fine? This is your take home question. You can just go and work out, maybe a small paragraph you can write and submit. Okay, fine, that's all I have for today. No attendance, you can leave.